coupled oscillators. So there's a bunch of important stuff with a coupled oscillator, but we're going to start with the simplest case to understand what's going on, and then we can do some more complicated stuff later. So in this video, I'm going to take this system. We have a mass and a mass. They're identical masses. We're going to have two springs on the outside that are identical, and then this one in the middle, I'm going to allow that one to be different. Okay, so we have two spring constants K, and the middle one's a spring constant B. So this is the simplest you can get. And we want to find the equation of motion from this and see what we can figure out. And it's going to be great. And then we'll do weirder cases later. Okay, we're saving this for just the normal, simplest case. So the first thing I want to do, I want to get the equation of motion for the system in one dimension. I have two variables, right? I have the position of mass 1 and the position of mass 2. And they both have mass m. But let's call this is the equilibrium position, but I'm going to call this distance right here x1. Is that out of the frame? No. And I'm going to call this x2. So if this, as x increases, that mass moves this way. As x2 increases, that mass moves that way. And now I want to write down Newton's second law in the x direction. Okay. So in the x direction, we can write that down for mass 1. I'm going to say F net x. Okay. So there are two forces on the system. There is the force from the spring right here and the force from that spring. And in one dimension, I can say that as this moves that way, that spring's going to pull back that way in the negative direction, and it's going to be a force of negative k x1, right? So if you move this over a little bit, that spring's going to pull back that way. If you move this into the negative direction, it's going to push that way. Okay. Now, suppose I keep that one fixed, and I move this mass this way. Well, I'm going to compress that spring an amount x1. And if I do that, there's going to be a force pushing back this way. So I get minus k of b times x1. However, what if this mass moves too? What if both of these masses move the same amount? Then that spring would not be compressed or stretched, so they would have no force. So this depends on not just the position of x1, but also of x2. So let's write this. And I always get this backwards. It's fine to write it out and then think about it. So imagine x1 is 0. I get negative b x1, which is what I expect. Imagine x1 and x2 are the same. I get 0. So right there, we're pretty much on the right track. Now imagine that x1 is stationary and I pull this one that way. Well, if I do that, then this is going to stretch. It's actually going to pull the mass that way. So I get a negative, and negative is a positive. That seems to work. Okay, now, and that's going to be equal to m x1 double dot. Just a reminder, this is classical mechanics. So I shouldn't have to say this. I'll put it way over here, way over here. x1 double dot is the second derivative of x1 with respect to time. Dots are derivatives with respect to time because it looks cool. We like to make things look cool. Now let's do the same thing, F net in the x direction for mass 2. Okay, so mass 2, if I move this way, if x2 increases, that's going to compress that spring. So the spring's going to push this back this way. So I do get negative k x2. And so you have to be careful because that doesn't seem like that's what it would be, right? Because the springs, you're compressing the spring, but it's on the other side of the mass. Now imagine that I move this way. We're going to do the same argument, and I hold that one stationary. Now I'm going to stretch that spring, so it's going to pull back. So I get minus b x2. Now if I move both of those, let's just try this. So if I move both of them the same amount, that's 0. That makes sense. If I keep that one stationary and I move this one that way, it's going to compress it and push it that way. So that does give me the right answer. So I'm pretty sure that's right. And it's going to be m x2 double dot. Let me just double check. x2, yep, got it. I wrote it down because I knew I'd make a mistake. Now we have a situation here that we want to solve these equations. There's a couple ways that we could do this. Let's just first look at the situation. Okay, here I have a bunch of stuff going on. What if I'm going to write this out long term. So I'm going to write this as m x1 double dot double dot equals this negative k x1 minus b x1 plus b x2. That's the same thing. I just multiplied it out. And then I have m x2 double dot equals negative k x2 minus b x2 plus b x1. Now, just for fun, let's add these together. I'm going to add those two equations together. So if I do that over here, I have equals m x1 double dot plus x2 double dot, right? If I add those two things, I can factor out the mass. And then over here, I have minus k, x1, x2. So this is going to be minus k x1 plus x2. And then I have minus x1b plus x1b, cancel. And then I have minus b x2 plus b x2, cancel. OK, so that's it. So that's my equation. I need that. I'm going to need that later. Let's put that over there. I'm going to write this as, I don't need this thing, but I do want to preserve some things. So say m x, I'm going to mess up those forces. x1 double dot equals negative k x1 minus b x1 minus x2. And then m x2 double dot is negative k x2 minus b x2 minus x1. That's what I have. OK. And then this equation, we can deal with that. Just to rewrite it, m x1 double dot plus x2 double dot equals negative k x1 plus x2. Well, that looks nice. Let's just say that y1 is equal to x1 plus x2. I'm going to do a use substitution. If that's the case, and I take the derivative, y1 dot is x1 dot plus x2 dot, y1 double dot is x1 double dot plus x2 double dot. So this becomes m y1 double dot equals negative k y1. What? I know how to solve that equation. So now we're back to a simple harmonic oscillator in the variable y. We can just guess the solution and check and see if it's right, and it is right. I'm going to say y1 is equal to a1 cosine omega 1t plus phi 1. And we can find a1, omega 1, phi 1 from the initial conditions. And I'm going to keep the simplest initial conditions for now, right? You can make it more complicated. But how do I find these conditions? Let's do it for x1 or y1 and do simple cases. So imagine it starts from rest. So the initial velocities are both 0. Okay. Actually, we'll get to that in a little bit. We'll solve for y2 next. Okay. So that's important. That's one solution. But I only have one variable to represent two objects, and that's impossible. So now let's go back to our equation over here and say subtract them. So what happens if I subtract those two values, those two equations? So if I subtract them, I get m times x1 double dot minus x2 double dot. And then I have negative k x1 minus negative k x2. That's going to be equal to negative k times x1 minus x2. And then I'm just going to subtract the rest stuff. I'm running out of room here. Let me just scooch this down. So I have m x1 double dot minus x2 double dot equals negative k x1 minus x2. And the other ones I'm just going to do manually. Well, let's see. So I have negative b x1 plus b x2. So I can actually write that as negative b times x1 minus x2. I factor out the b. And then here I have plus b times x2 minus x1. And you'll see that I can switch the order of that and it becomes negative, so I have two of those terms. So this is going to be equal to negative k x1 minus x2 minus 2b x1 minus x2. And now I have x1 minus x2 double dot, x1 minus x2, x1 minus x2. And so now we can make the second substitution that y2 is x1 minus x2, and y2 double dot is x1 double dot minus x2 double dot. So if I make that substitution, I get m y2 double dot equals negative k y2 minus 2b y2, or negative k plus 2b y2. Again, we are at the case of a simple harmonic oscillator. We have a different spring constant here, but we have essentially a constant. We have a mass, second derivative, negative constant times y2. Again, we can guess the solution. I should point up here that in this solution, this is true only if, when I take the derivative, omega 1 would have to be equal to omega 1. I can put it right here. Omega 1 is the square root of k over m, right? Because I had k and m. And then down here, y2 is going to be a2 cosine omega 2t plus phi 2. And this will only be true if omega 2 is equal to the square root of this, k plus 2b over m. All right, so they have different frequencies of oscillations. But now we have two solutions. Now what do we want to do? Well, I do want to find the initial conditions, right? I want to find A1 and A2, phi 1 and phi 2. So let's just start with phi 1 and phi 2. So let's say that, remember, y1 is equal to x1 plus x2. So y1 dot is x1 dot plus x2 dot. And if I start those two from 0, then y1 dot is 0. And I can do the same thing. y2 dot is x1 dot minus x2 dot, and I'm going to start those from rest 2. So now let's go up here and take the derivatives of our functions. y1 dot is going to be negative a1 omega 1 sine omega 1 t plus phi 1. And so if y1 dot is 0 at t equals 0, then this term is 0, and the only way for it to work is for phi 1 to be 0, or a1 to be 0, but that's not going to happen, right? So if that's true, if they're in opposite directions, or they're 0, there's actually more than one way, then phi 1 is 0. We could do the same thing. Phi y2 dot is negative a2 omega 2 sine omega 2t plus phi 2. And if I let t equal 0, and y2 is 0 and t is 0 at t equals 0, the only way for that to work is phi 2 to be 0. So now I have phi 1 and phi 2 is 0 if I start the objects from rest, which I will do. Okay. Now, how do I find a1 and a2? Well, let's go back over here. Let's delete this stuff. Okay, so y1 at t equals 0 is a1 cosine of omega 1 times 0. I've already said phi 1 is 0, so that's 1. So this is going to be equal to y1 0, the initial y value of 0, okay, which I don't know because I need x. And the same thing for y2 0 is going to be a2 cosine omega 2 0, and that's y2 0, the initial y value. And so we can pick some values here. So yeah, y1 0 is x1 0 plus x2 0. y2 0 is x1 0 minus x2 0. So if I know the initial values, I can find those. I can find my initial conditions, and everything will work. Okay. Let's do this. And I'm going to actually do this two ways, right? So now I have a solution. I have a solution for x1 and x2 because I can solve back over here. If I want to go back to x's and x1 and x2, I can see that x1 is going to be 1/2 y1 plus y2, right? Because y1 is x1 plus x2, y2 is x1 minus x2. So if I add these two terms together, I get 2x1. So I have to divide by 2. And the same thing, I could subtract them. x2 is going to be 1/2 y1 minus y2. Because if I take this minus the negative of that, I get this. But now I have equations for y1 and y2. I know how it's all going to move. Okay, it's kind of cool. Now, there is another way to do the whole thing. I could do the whole thing numerically, right? I could calculate the acceleration for mass 1 from these position values. I could calculate the acceleration for mass 2 from these position values. I could break it into small time intervals, use that to update the velocity, use the velocity to update position, and redo it again and again and again. Let's just see what would happen, and then I'm going to show you the special case. So here is an animation. I'm not going to go over all the details. This actually uses this method, okay? But we could plot these two and see they're the same thing, and I'm not going to do that. But I am going to show you. If you want to know how to build this whole code, I will happily show you. But here I have mass 1, mass 2. I have two identical springs. The middle spring is different. That's why I drew it a little bit different. But I'm starting with some initial positions. And you can see they move around in some strange situation because I have the sum of these two functions. And you can plot that. In fact, here is the plot. So this is the plot of one of these is the numerical calculation and for x2, and this is x2 theoretical. And I shifted it up just so you can see that they are indeed identical. So these two position functions for x2 calculated the two different ways are the same thing. Down here, this is x1, and they're calculated the two different ways. But they're the same function, right? I shifted it so you could see that they are the same thing. So it does indeed work. Now let's think about the special case. The special case of what if I want a2 to be 0? And how could I make a2 equal 0? Well, a2 is equal to 0 if y2 is equal to 0, which means up here, if x1 is equal to x2, then y2 0 is 0. So this means if I start these with the same position, then there is no function right here, and I'm just left with this. I'm just left with that function to oscillate my masses. And that means that they would both have the same angular frequency, and it'd be the same as a single mass with a single spring constant. So let's just go ahead and animate that. I'm going to give my two masses initial velocity of 0. I'm going to shift them over the same amount, and I'm going to let it go. Let's see what happens. So here is actual Python code. Down here, I have x2 dot is, I'm going to put it at positive 0.03. And let's run the code. And you will notice that the two masses, the middle spring is never stretched or compressed. So the two masses are essentially independently oscillating back and forth on their own. So this is just a single mass with a single spring. That's a single mass with a single spring. We know the solution to that, and that's important. Okay, now let's go back over to the board real quick. What if I want a1 to be 0? Well, a1 would be 0 if y1 is 0 at 0, and that would mean that the sum of x1 and x2 is 0. So one way I can do that is to take you could do it with initial velocities too, okay? But that's just a little bit more complicated. So I'm going to take this one and let's say move it over here and move this one in the opposite direction. So when I add them together initially, I get a 0 y velocity, y1. So I'm going to take these two and give them negative x values. Let's see what happens. But I would be left with this solution. That one's 0, right? A1's 0. So this should have an angular frequency of omega 2, which is different than before. Let me switch over the code and just show you. We can actually just see. I'm not sure why those two are different. Oh, because my two different. Okay, so the blue and the red are the numerical ones. That's one I changed. I didn't change the other one. But you can see here that this has a period of 0.763. Now, when I change it to the other situation, this oscillation, we should have a different period. So up here, going back to the code, I'm just going to put a negative sign in front of x2 and run it. And now, again, they have the same frequency. They're out of phase, but they're the same frequency, and the middle spring is stretched. So they're not independent, right? But they are moving in sync. And if we look down here, again, ignore that top curve, I have the period of right here, 0.528. So it is a shorter period, higher frequency, right? Higher frequency, which is exactly what we say over here with omega 2. These are called our normal modes. Right? Normal modes are the two solutions that we can get here. Now, you can't do it if you have some weird combination of masses. You can do it. I'm sorry, you can. You can't do it this way. So imagine all these are different masses. M1, M2, K1, K2, K3. There are still normal modes, but you can't do this method to find those normal modes. You can't add the two solutions together and expect to get anything to happen, right? If I have K1 is different than that one, and when I add those two together, I'm not going to be able to factor it out. I'm not going to be able to get a nice value. But we can still do it. There's another way to do it. I'll talk about that on another video, but we're going to show you how to find these normal modes, because if you find the normal modes, you can represent any other motion as a linear combination of normal modes, and that's what makes it so powerful. And so you can do it for very complicated systems. You can even do it for systems that have more than two masses. But we'll do that later. That's your introduction to normal modes and coupled oscillations. The end. I'll see you soon. Notice I didn't say I'll talk to you later. I said I'll see you soon. I just thought I'd change up a little bit. Okay, bye.